All right. Hello, everybody. This is going to be right about time to start. My name is Gavin. I am, one of the organizers for this session. This is the HPC RSE SIG meetup. And so for this introduction, I just want to go through what we're going to be covering. Just to confirm, can everybody hear me clearly? Yep, perfect. All right. So this session, we have quite a large amount of things going on. So the first 10 minutes is the introduction and welcome. Introduction and welcome. Then we've got a series of presentations for technical and exascale presentations. Then those speakers plus a few others will be sitting on a panel where you can all present your questions towards them. And there'll also be another panel in the future of UK HPC service panel. And most questions can be presented via Slido. There'll be a lunch. Then we'll be doing HPC community and training presentations. And then that will also be leading into another panel session. We'll have an interactive survey at the end with a wrap-up. So to go through a bit more detail about the panel discussions, during each panel we'll have an open seat. One of these seats there will be made available, and this is open to anyone in the audience who is interested in taking part. Please take a seat. We are preferably looking for people in their early career to come forward and present their ideas, their viewpoints. Everybody here's opinion and usage is valid, and we want to just hear a diverse range of opinions. So if you see the empty seat and feel willing to step up and sit down and just hear some of the questions that have been answered, please do so. And it'll be a great opportunity, and you can introduce yourself to the wider RSE HPC SIG community. Whilst we are going over this, just a few things about code of conduct. In this discussion, there'll be lots of range of opinions. Please be respectful, welcoming, and inclusive of everything that's being presented. Try not to disrupt or interrupt any of the comments and questions that are being asked and responses. As with the RSE Code of Conduct, no violence, no sexist, racist, homophobic, transphobic, ableist, or exclusionary jokes or remarks in this session. Please don't make fun of any programming languages, technology, or platforms. People might feel uncomfortable. And if you break the Code of Conduct, you will be asked to leave. We tend to follow the Chatham House of Rules for discussion. So here's what it says here. When a meeting or part thereof is held under the Chatham House rules, participants are free to use the information received, but neither the identity nor the affiliation of the speakers, nor that of any of the participants may be revealed. Means talk about what they're saying, but not who and from where. And just to give you an update of what's happened over the past year with the RSE HPC SIG, we have become one of the official RSE Society special interest groups. You may have seen the presentation before on the list of special interest groups. We are one of those present. We've got a mini website. It's here. We are constantly adding information, adding updates on what's been happening. We've got our terms of reference. Those of you who are part of the mailing list may have been seeing the messages about the update in terms of reference. We're trying to update it and get feedback from the community to make sure it's all up to date with everything that is happening. And just to give some information on the initial steering group members, and thanks for them for helping set everything up. And my name is right here as an addition. I joined during the first half of 2025. And we've done some of certain other tasks, such as presented at HPC SIG, and we're looking forward to other ways we can collaborate with them. And I've got the HPC SIG shirt on as a showcase of our connection. We had an online meetup on May the 19th, and that was great to see a lot of presentations and part of the work that's been done. And we had an in-person meeting during Durham HPC Days on the 5th of June. And I believe the event outcomes for this entire session are to present understanding to the current state of play in the field of HPC, information on the current state of HPC services and future plans, and understanding the topics of interest across the HPC community, all of you, and the wider community's opinions on this topic, and to form personal professional networks and peer support, especially for RSEs new to HPC. And that is it. So we will start off with the technical and exascale presentations, and the chair for that, please welcome Tuomas.
Hey everyone, so my name is Tuomas. I'm a RC at UCL. We've got two really cool presentations to set the scene for the discussions. And the first presenter is going to be Evgeny Belikov from EPCC. He's going to talk about performance optimization using hardware performance counters.
Everyone, my name is Evgeny. I'm based at HPCC in an RSE role. HPCC is the National Supercomputing Center in the UK. We look, among other systems, after Archer-2, down but not out. So it's still running at least until 21st of November 26. So can I have a quick show of hands who's using Archer for your work? I would like to speak about hardware performance counters as a way to have an insight into performance, but it's a very brief overview of a tool suite that is established called Liquid on Archer-2 because it's now available for a while. Does someone know what Liquid is? Okay, a few. So hopefully it will be interesting and it will be an addition to an RSE's tool belt. It stands for like I know what I'm doing. I think it's attributed to Georg Hager from Erlangen, Nuremberg, Rechenzentrum. It's a supercomputing center in Germany, a regional center. And they're behind, mainly the developers behind this. So Liquid is a mature tool. And the motivation behind this, often we want to look at performance. Once we know our simulations are correct, we want them to use the resource efficiently. And we go through the cycle of defining an area of interest, maybe instrumenting the code, measuring, analyzing results, improving, and so on. So Liquid is one of the tool suites that can help us with this. And often we'll look first at the runtime. But the runtime only tells us where we spend time in the code, but not exactly the reason why it might have slowed down once we did some code changes, for example. And hardware performance counters give us some extra insight into means-based metrics. So hardware performance counters, they are actually registers on the hardware that, for example, hardware developers use to debug their hardware. But we can also make use of this to optimize performance. So usually it's a small number of registers, and some are programmable, some are fixed, and they track something like cycles, retired instructions, bytes moved from or to memory, things like that. And another reason is that because we've got this non-uniform memory architecture in our machines, most of the codes are memory bound, and this is an interesting area to look at to get numbers that help us quantify performance in more detail using, for example, operational intensity of our loops. And Liquid is an open source portable suite of command line tools that we can use, and I'll briefly mention a few of those. So this should be just a kind of very bird's eye view sort of talk. On the right-hand side, there's like the stack, and we will mainly touch on the left upper corner in the command line tools. But there's also an API. You can link the Liquid library and do quite magic things with it in very different ways. It supports GPUs, but I'll not cover that. What else can we do? We can pin processes. Briefly mention that, and we can mark certain bits of code. So the advantage of Liquid is that it can run without the need to recompile and edit your code. But if you need to more surgically look at only a particular section of the code, then you need to recompile. So if I run this tool called Liquid Topology on an Arch-2 node, we can get output like this. It's ASCII text, but it's quite useful. We can see the thread IDs that are then used for pinning. So we can see on Archer-2 we've got an AMD EPIC processor with 2 sockets and total of 128 cores. Then we can see on the one processor of those 2, we've got 8 NUMA domains. Those correspond to core complex dies in AMD terminology. So those are usually connected to a memory channel. And then within those, we've got further hierarchy. The core complexes are then groups of 4 cores that are associated with last level cache, and so on. And for optimization, at the very detailed level, these are all details that might be useful later on. One thing the liquid documentation refers to is this topological entities. So they define a convenient way to pin processes and define kind of this hierarchy level. So we can refer to the whole node as N, S as the socket or memory domain. This would correspond to the NUMA domain, and C as the last level cache. So here's an example of using this liquid pin tool. If we call it, it's in the middle of the slide. So liquid pin minus C, and then we have some complicated syntax. And I refer you to the docs because there are very many ways. You can define a stride, you can define. So this example says on socket 0, I want to place 4 measurement threads on measure on the threads hardware thread 0 to 3. And then on the second socket, the same. So those 0 to 3 are logical threads on that topological entity. So it's quite handy. Otherwise, you need to go back to this and find the number you want. So you can always, instead of this, specify the numbers, like a list of long list of numbers. But this is a more short hand syntax. Next tool is liquid perf counter. This is the main kind of workhorse for node level optimization. And it's got multiple modes. I'll mention mainly the wrapper mode. So it wraps your application and measures the performance counters during the runtime of the application on those cores on which you specify using this liquid pin notation. There are also other modes that allow you to measure, regardless of the application, on specific core for duration or in time intervals to get the timeline. So it's very comprehensive in the way, so flexible, and in most cases you don't need to recompile your code. So the only requirement is that it's dynamically linked because of the how liquid then intercepts the library call and inserts the profiling, like the instructions to get the counters. And this is the main workhorse on Archer2. So because we've got multiple nodes, there is another wrapper called liquid MPI run, and Arno Promem at HPCC did some implementation to customize it to fit well with how Slurm configuration on Archer2 works with it. So we've got a centralized module. So you can type module load liquid, and then you get the custom liquid that works well on Archer2. One other thing to mention is it defines different, again, I refer to documentation, but something like flops DP, mem, branch, this will be the event groups to monitor. So if you're interested in floating point operation performance for doubles, you use that group. If you're interested in memory, you use the group. You can define your own group because in Liquid, it's Lua based mainly, and you can have like textual files where you define your own metrics as well, derived from the core metrics. And it aggregates statistics. Let's have a look at the output in a moment. First, just a quick reminder of the kind of options. I wanted to make the slides available and self-contained, so you can look it up later as a recipe. So we can specify number of processes, the pin list, then the G specifies the performance event group to monitor. The new thing in the customized version is this no CPU bind option. We need to use this on Archer2 for it to work well with Slurm, the scheduler. Okay, and a few other things. -M is important for this marker. I come back to this in a moment. This is an example of a job of Slurm's submission script for a small job using 2 nodes, fully populated, and we've got this kind of SBatch hints. You need to use your own account here instead of the 19. And this hint no multi-thread and distribution block, this is the common way to pin processes on Archer2. So you still need this. So this is where Liquid comes in, module load Liquid gets us the Liquid XT High is another application we can use to check where our processes run. So I use it as an example here. And then when we run this on this example with 4 threads on a single node, we get the output like on the right-hand side of this box. It just tells us it does run on where we would expect it to run for the simple example. But the idea is on a single node, we don't need to use a liquid MPI run. We can use perf counter directly. And then with the pinning syntax here, I'm specifying pin on the first 4 core complexes, group of 4 cores, and this corresponds to those numbers. And this is what we see in the output. So it gives us a way to specify at the fine grain where to look for numbers. And this is what we get as an output. It's also textual. There is an option to get a CSV file with $O. And we can see we get a lot of numbers. So often the tricky part is in interpreting them for your application and your use case. But in this case, for each thread, we've got the counts. And these are the counter names, the PIX, PM, or PMC. The PMC are the programmable counters. And finally, we get for the metrics, like the runtime, the clock, the flops, kind of a summary. Usually it's sum, the min, the max, and the average. So then you could look, for example, do all your threads have the same number of instructions they worked on? Maybe it's a load imbalance if it's not the case. Any questions so far? So that's quite a quick run through, but I hope you can see how this might fit into your investigation into performance. So perhaps you're looking to see whether some part of your computation is idle. Or if you suggest an optimization and you suspect that it improves memory traffic or reduces the number of, let's say, branch mispredictions in your core loop, you can see in the counters, does it actually do that? So it adds a more detailed level of means-based metrics. I'll skip over this. This is another example where we can use a hybrid MPI class OpenMP code. But the main thing that changes at the bottom is we need to specify the number of threads per process. Any question about the basic tools? This is just a very small subset. Yes, please.
Does Liquid also support like drill down analysis where you like aggregate like multiple like performance counters to see if the front end or the back end of the CPU is like a bottleneck, and then like drill down to the specifics later on, like to get an overview of this?
So you can get per thread information. You can measure on only specific areas depending on the counter. I think you can do this. I can't off the top of the head tell you how exactly, like what flag you need for this, but I would say it's possible. So there are 2 more things, and I'll spend only a minute on each just to summarize. So Marker API allows it to drill down in a way, not in the way you mentioned, but in the way to define a section of the code, and you need to then rebuild your code with this, with the flags to get the library in. And then this is a C example. We include the Liquid Marker API, then we mark the init, mark a register with a string, and then the region of code you're interested in measuring, the hot loop, you put the marker start and marker stop after that. And then you get counters for that particular region, not for the whole application. And finally, you can work with the roofline model. It's also a very brief introduction. So you can look at flops for performance for an application and its operational intensity. And you could get those numbers using Liquid. So you can first define the slope line, the bound based on memory bandwidth, through running stream or Liquid benchmark that does the same thing. And then you get the bound based on performance. This you can get from number of cores you have times the clock frequency. And then you can see where is your application located. If it's on the left of the reach point, then it's memory bound. So you need to look at optimizations for memory. If it's compute bound, it would be in the right-hand side region. And as the further away it is from the lines, the more optimization potential there is for your loops. There's I'll skip over this, and there are some gotchas. We can discuss those next. But very brief overview. Please look at our recording from recent webinar. That's more details, and then there are Arch2 docs, and please get in touch. And let's have maybe a couple of questions if we can fit out.
Does liquids do energy measurements?
Yes, there's -G energy can give you something. This depends on which counters the architecture provides. So on Arch2, we can get the package energy, but not per core counters, if I remember correctly.
Next up is my colleague from UCL, Mose Giordano. He's going to talk about running simulations on thousands of GPUs in Julia.
Hi everyone, I'm Mose Giordano. I will talk about this new framework that we are developing in Julia called the Reactant for accelerating scientific code and running on different kind of accelerators, not just GPUs, but also TPUs, and we are working also for targeting other accelerators. So first of all, this is a collaboration with many people. Is a list of people that we work with. It's not just academia, it's also industry. So we got people from Google, MIT, NVIDIA, and many other companies and universities. And this was all led by Billy Moses, who is a professor at the University of Urbana-Champaign and also a researcher at Google. So let's start from the scientific problem that we use as a motivation for this work. And this is oceanography. It's a ocean model, which is it's a state-of-the-art model. It's been already tested and scaled up to 768 GPUs. There is a paper if you want to have a look, and it demonstrated very good memory and energy efficiency when running the model. And also there are some cool pictures from the paper if you want to have a look, and you're curious about the scientific results of this model. But why we may want to improve set of things. So LLVM is a compiler framework which is used by most compilers that are out there, like all the vendor compilers nowadays are going to use LLVM. The problem of LLVM is that when you compile for a GPU or any other accelerator or any other device, this separates physically the module for the host and the device, and they cannot talk to each other, or you cannot really move code between the host and the device. It's just fixed. Whatever you have on the device, it's just this cannot be transferred and optimized and moved to the host. And also LLVM is very low level. It's kind of a slightly more readable assembly, but it's very low level and doesn't have information about parallelism and loses information about structures and many other things. So yeah, it will be better to really nice to have better ways to deal with all these problems and better optimize the code for you. Also, if you look more deeply at the scientific code, so this is a stencil problem, and in shenanigans, we actually have about 170 stencil-like kernels like this. And if you squint very hard, you will notice that a stencil operation like this is actually a convolution. And it turns out that accelerators like TPUs and GPUs are very, very, very good at doing convolutions. They are actually created just to do convolution neural networks. So it will be very nice if your friendly compiler was able to take this kind of human readable code and turn it into a call to a convolution without you, user, having to think, oh, this is a convolution, I need to do a convolution call, which is not nice. So how we can do this? So MLIR is another compiler framework based on LLVM, but more higher level. And before people get confused, ML stands for multi-level. It's not machine learning. So it's multi-level intermediate representation. And it's MLIR is very useful for this because it can preserve host and device code altogether. So it's a single module. It's like this module on the right is what MLIR gets you out of this C++ code. And since it's all together, both the device and the device code, you can do optimizations like you have a sum, which is actually a constant of over these for loop somewhere. Yes. So this should be yes. So this is a sum that you can take out of the kernel. But if you forget to do it when you write your codes, the compiler will not be able to do for you in LLVM because it cannot. But in MLIR, since it's a single mode, you can take out the sum out of the for loop, and this now becomes a constant, and it avoids doing useless computations for you. So yeah, MLIR can optimize between the caller and the kernel. It knows about parallelization. So you can give it single node scalar-like code, and it will be able to parallelize it for you. And also, if you're interested in machine learning, maybe you want to do differentiation or automatic differentiation, and improving the performance of your primal function gets you a much larger speed up on the derivative once you auto differentiate. So it's very important to be able to optimize as early as possible. Right, so this framework that we built for doing all of this basically takes, in this case, Julia, but actually I will mention later, this can be used also from other languages, gets Julia code in this case, compiles down to LLVM-IR, intermediate representation, then it's raised to MLIR, the multi-level intermediate representation, and then you can do all the automatic parallelization and automatic distribution of the code. So you can start from single node code, and then you can automatically distribute on thousands of accelerators. And then you can do further optimizations. So that, for example, in this case, again, you start from a standstill problem, and in the end you get a call to a convolution kernel in CUDA or AMD or whatever the accelerator. The front end that we built is called Reactant.jl. It's a Julia package. You can think of this as a front end for MLIR. You need to annotate the codes to the function that you want to accelerate with this fgit macro, but importantly, these are done at the call place, not at the definition place. So you don't need to change all your code, all your packages that you want to use to do this. You only change the call place, which is much simpler. And also this framework takes a lot of advantage of Julia multiple dispatch and abstract interpretation. So Reactant.jl supports non-pure and mutative functions and arbitrary Julia code. It's not a DSL. You can, like Oceanigans, it's a code that has been already written for ages, and we didn't have to do many changes just to use Reactant. It does tracing into equivalent stable HLO. It's a MLIR dialect, that's called. Can do automatic buffer donation to optimize memory reuse without you having to write this specifically. Can do distributed computing via sharding or MPI. And you can ask me about this later if you want, because I have backup slides. This enabled a very large code reuse, because again, you don't need to change your code, or not as much code in your libraries, but only when you call it. And you can raise CUDA kernels. So Oceanigans has CUDA-like kernels, but we were able to run these CUDA kernels on TPUs, which is a completely different accelerator. And you can also do automatic differentiation via enzyme, which enables the paradigm of optimizing first and then differentiate, which again is very important for getting super fast derivatives when you do machine learning. There is a talk about this at JuliaCon. It was a couple of months ago. This talk is basically a shortened version of that talk. Yeah, we ran this on TPUs. This was 1200 plus TPUs. Got a large number. By the way, this is more than 1 exaflop. And you get this on Google Cloud. So we got this allocation of 1.2-ish bflow 16 exaflops. And yeah, so this is not very super optimized yet. We were just at the beginning focused on make it run and then try to get it faster. So this is the plot for make it run first. So it's not super exciting at the moment. Like, it's not flat, but we would like to have it flat at the beginning. But yeah, there was a jump when we went from one pod to multiple pods to show the network communication. To conclude, Reactant is an optimizing compiler framework written in Julia and built on top MLIR. It preserves high-level structures from Julia to the compiler. We demonstrated it's very effective at optimizing generic scientific programs. It doesn't require rewriting your code into DSLs. We demonstrated it is able to retarget code from like a CUDA-like code into some other accelerators. Actually, for this talk, I wanted to test this on AMD. So last week I made it work on AMD GPUs. We can already use it on GPUs, and we are planning to support other accelerators like Tenstor and some other ones. Under the hood, it leverages XLA, which is a compiler framework used by all the runtime, used by all the machine learning frameworks like TensorFlow, JAX, and PyTorch. This is why the collaboration with the industry is very important. It is compatible with mutation, control flow, automatic differentiation, and lastly, the backend used by Reactant is called enzyme JAX. And it can also be used by C++ and Python. So if you don't use Julia, you can also start looking into this to accelerate your code. This already demonstrated 50% performance in a Google Gemma model using 32 TPUs, I believe. And this is all open source. It's on GitHub. You can have a look. You can also play with it on Google Colab using both TPUs and GPUs. And I think that
Thanks for your talk. Great work. I was wondering that you mentioned differentiation, right? Like, do you inject like the respective code like at the IR level? Like
yeah, so Enzyme is a autodiff engine which works at the LLVM level, but for this work can also differentiate MLIR. And yeah, the idea is always to differentiate after optimization because again, you get much faster derivatives.
okay, thank you.
Differential equations. We didn't try much differential equations.jl, but it's used a lot for machine learning. Like there is a Julia framework for machine learning called LAX.jl, which uses Reactant. Yeah, I don't know if anyone has tried yet with differential equations.
Maybe just a brief question. I have a Julia script. I have a computer return. So the plane, if I use library, I just annotate it in the automatically use the accelerator divided by the.
Yeah, yes. If you have on the system, yes. And if you have multiple of them and your problem is very large, you will do also automatically the distribution, like all the parallelization. It introduces for you the communication. So GPU communication is done via NCCL for NVIDIA and the one RCCL, I think it's called the AMD one. And internet communication can be done by either gRPC, I think it's called, or MPI. If you have MPI, you can also use MPI for the internet communication. But GPU on the same node is done by NCCL. So maybe, yeah.
I see on your README that there's a header saying that you warn everyone that the API is subject to change.
Yeah, it's still in development.
Do you have any idea of like in which timeline you're gonna be to have an API that can be used by the large mass?
If you're very scared of breaking changes, maybe come back in 1 year-ish. But people are already using it now, and
they're not complaining of like changes that were it's already pretty usable as it is.
Yeah, like many people, I know people are using it for like quantum simulations for the tensor operations. They use it, and they've been using it for months. And yeah, so this is basically a alternative compiler pipeline to Julia's compiler itself. Maybe in the future, Julia compiler will actually use MLIR because it's a technology that the industry is adopting very heavily. But at the moment, it's kind of an alternative. So, but it also takes advantage of the fact that the Julia pipeline enables abstract interpretation. So it's building on top of the technology which powers Julia itself. And so this is very important. And LLVM doesn't go away completely because, again, what this framework does is first take Julia code, compile to LLVM IR, and then get it back to MLIR. So it is still important to integrate with this.
Okay, shall we do a quick Thank you. Okay, don't go anywhere. So then I would like to invite Evgeny back and Alex, and I would also extend an invitation to the audience. We have 2 empty chairs, so if you would like to, if you have opinions, if you would like to join the next discussion, please feel free to come over here and introduce yourself. Yeah, take a chair. Well, we're going to take questions from the audience. It's going to be technical topics related to our HPC RSE work. I was planning to start with the CI/CD topic, and then we'll go from there.
You can also drop in and out, so if you want to join later or leave your chair because setting up, that's fine as well.
Okay. Well, okay, we will. Okay, would you like to introduce yourself, Alex?
Hi, yeah. These are fantastic talks. I'm Alex. I didn't do a talk. I'm just here as, I suppose, also an early career RSE. So I've been an RSE for about 1.5 years. And in that time and in previous work, I've had a fair amount of experience with HPC. Recently, that there's been some work trying to accelerate code using GPUs on Baskerville, which is the tier 2 HPC we have access to. That has been primarily in Python using the JAX library, which some people might be familiar with. And I think that's probably about it.
Okay, thank you. Okay, so we have about 20-25 minutes to talk with these guys, and then we're going to swap around and ask some other panelists to come and talk about the future of the UK HPC landscape. But the idea is that in this first session, we'll try to keep the discussion to sort of RSE software topics, and the second session is perhaps a bit more sort of strategic, future-looking session. So I'm gonna try and pick up on some things from the talks. So I mean, I really liked the hardware performance counters you talked about. As an RSE, what I would really like is that it's integrated into my CI pipeline, so that when I push a code change into my code, my CI would come back and tell me, you are now twice as fast on Archer 2, for example. What do you think this is feasible? Do you have any experience with this kind of things? What barriers are there?
I think this is feasible. Some technical issues might be about where the CI runners run and how to access them, and this is a discussion about security with our systems team. And but in principle, it can be done. I think it's important next step to sort of normalize this as also part of testing, that it's not only correctness testing, but there are also some performance tests that we can quickly catch regressions if someone messes with our hot loop and makes it 10 times slower suddenly, then this should be flagged up quickly. I mean, users usually then come and complain if something is broken, but that's like the last resort, so we should catch it before this happens. In terms of more specific approaches, maybe containers can help to have some kind of nailed down environment where you run it in. I don't know. If Nathan, you've got any comments on this?
Which parts in terms of approaches, how you could
we've got reframe tests. So,
Yeah, I believe we already have some frame tests that we run as a service, but that's all run directly through R2. We don't have any. We are still in the process of looking into how we could do a launching from a GitHub runner, because again, it's very authentication issue with the roster. There are solutions out there.
We've had some sensitive Giacomo.
Sorry, what was that comment? I missed that.
We've had success using Giacomo authentication.
I think I suspect when we do it, it will be through our safe authentication system, which we've used for other kind of web-based access to stuff. We get wrong code.
That's
Yeah, do you have any comment?
not maybe super insightful, but we found I've seen this question come up a bit in our group as well when we're similarly we sort of have security sort of requirements and limitations to the runners, and I don't think we have access to GPU runners in our sort of in-house GitLab instance or anything like that. So this sort of thing does come up from time to time. People want this in their CR, and tends to get a bit of pushback from people higher up when it comes to security. So it's good that it seems like it's a wider need, and other RSEs have also would like to do that, because we can take that back. And
Yeah, so can we as a RSE community do something about come up with something that we can take forward?
I guess there's always a concern if you're linked to a repo that you just end up executing arbitrary code on the system, right? And that's why people get quite nervous about doing this, is you don't know whether if you've got no direct link to the repository, who's committing. Then somebody could commit something that it's got an automated runner on a large scale system that could do something. That's you'd have to have some sort of almost like curated repository that you have control over, that you control commits to. We can get away from the whole point of what to do it in the first place.
I guess somewhat related. What's your opinions of having moving away from kind of GitHub but more self-hosted GitLab as infrastructure, which is a bit easier to integrate because you can kind of avoid doing it just with the web interfaces and have a bit more control to self-hosted. You can maybe even host it on something which connects easier to the HPC.
Makes some things easier, other things harder, because I have a problem with self-hosted instances of GitLab is that sometimes they're like getting access to the instance is under a login for the institution which is hosting it. So if you want to open an issue for the project, you cannot, because maybe you're an external and you cannot. I'm a bit worried of that solution, because it actually creates a barrier for external contributors. On the other hand, makes it things easier for the institution itself, because they control better who is contributing. So there is this tension, which I don't know if that's necessarily the solution. Also, like in GitHub specifically, there is an option in the settings which maybe addresses that to run all the jobs from external contributors requires approval. It's something. I would prefer something stricter, to be honest, but at least that's something. And I totally share all the concerns, because I totally know that this is a problem.
Yeah.
I just wanted to add, I think someone mentioned Giacomo in the room over there, but I went to some training. I've not used it, but I went to training. Well, I used it in the training. It looks great. It works pretty well, but I think it only really a solution if you have an internal GitLab, within a center with internal resources, where your GitLab users are set from some LDAP, which is the same as your username or there's something you can make between that and your HPC system. I don't think it will work for a lot of public, research codes that use by multiple institutions or HPC systems of different centers and things.
I know that Spark, for example, has a like the main repo is on GitHub, but then the runners are on GitLab, and they have a mirror which automatically syncs the contributions. So, but that's extra infrastructure that means
security. Jacomar handles that, and it does it very well, but it only really works for kind of internal only things.
Okay, question behind you, Simon. Who's first? Yeah. go
Yeah,
for it.
just kind of what Moses said, like in our center in Jülich in Germany, we have Jacomar and of course it's run in our like GitLab instance, but a lot of these public projects are on GitHub and they are mirrored. And then you don't have to be kind of like external, but then you just have to be clever on the targets on when the runner in your HPC system runs. So I think, sure, maybe having a mirror is the solution, but it's the solution we have now that works for several groups.
Can I ask, how do you do the security thing? That's the bit I mentioned, right? So how do you manage the fact that somebody could commit to the GitHub repository, gets mirrored into your GitLab, and then runs on the, and it could be any, I mean, I know you have, everybody has authorized users, they can run any code anyway, but this is quite different because you don't know who those people are, right?
Yeah, so I guess the teams, I mean, my project, I don't have the experience in that, but I guess in your like GitLab YML or whatever, you have different targets on when you run, not just for every PR that happens on GitHub, you know, it would run, right? So you have to be a little bit more tricky on when that runs on your system.
Okay, so maybe I don't know. No. So can you trigger only certain actions based on who approved the commit? So if you had a relationship with the commit approver, then I know this person, I trust them, then the test can run.
That configuration is stored in the repository and can be edited by a PR.
Yeah, but this is why I should have the option to require approval from all the externals. Because yeah, I also don't like that. Well, I like it on one hand. On the other hand, anyone can edit it.
I was going to say, well, at some point, someone could say yes, you're going to put that, you're going to merge that. That's the only way you can stop malicious action.
I guess to some extent, is it a level of just governance of instead of our typical systems team accessing what users can access the system, we're handing that over to providers like GitHub by saying these users can access the repository. And I think there's an inherent risk there because there's no direct link between that user and their HPC account. And getting that link to exist, then you've effectively got two people managing authentication, which means the systems team will be happy for whoever is managing that GitHub repository that these users are behaving sensibly and doing authorized things. Is that to some extent the risk of them being actually active?
I don't know who was first, Simon.
Well, just a kind of suggestion. I think these are all connected together, and it's coming to the situation where you're kind of thinking you need to have concepts of development versions and production versions, and to perhaps have different criteria in terms of updates and running the tests according to those. If you're just developing a code and it's all fun and putting it around, it doesn't matter. If it's a code that's on an HPC system that's probably being used in production by some people, then to have a couple of version branches, whatever, that have different privilege attached to them and different risks.
Yeah, Martin.
Yeah, so when people are worried about sort of this, okay, we've removed our gate for keeping people who can run. Like how much of this can we sort of handle by more strongly isolating workloads? You know, when we're sort of thinking about like containers coming in or something like that, because I think there's two bits. Like, is someone using a lot of resources, and are they the right person? You know, am I comfortable giving the GitHub admin, you know, to say, look, you've got access, you control who comes in, or are we worried about random code coming in? Because I think both of those are, you know, they don't have to be related. Like, I think the solutions to those would be orthogonal to each other.
I guess the bit of the problem is what you're testing, right, and how users use our system. If the users are not using the data, you're not doing the right sort of CI
You're not doing
Yes.
the right sort of test.
But what I mean is, I meant in terms of isolating things. So, like, let's say you're running an isolated Slurm queue. You know that worst case, like the Slurm queue gets compromised somehow, it's not going to like affect the rest of the system. The user sees a Slurm queue. Whatever you use to isolate might be something else. But like you kind of bounded the consequences of that.
I think the things I think are that even in an isolated Slurm queue, and most HPC systems is the shared file system. So there's shared file system access and there's shared interconnect access with no security, essentially in the system. That's how you make NPI go fast. You turn off all the network security to a certain degree. All use function that don't go through that pathway, right? So how would you isolate them from that? One way to do it would to have a dedicated test mini system that has its own file system, and replicate the hardware and software configuration. So compromise will happen, right? It's just to let the system be turned out and think about it. So
this sort of data isolation on the shared storage is one of the gnarly problems we're kind of tackle with this HPC on TLE and HPC thing. So I'd love to chat to people who are thinking about that on their systems. Feels like something where there's some answers on some systems now, but maybe also stuff we can do when we think about version next.
Yeah, I think I'd like to argue that probably having PRs triggering CIs on the cluster is maybe not the best idea, because you don't want to waste all that resources for random stuff like, oh, I changed the white space now. So you kind of want to maybe have that more like actually approving merges. So like before it gets merged, it will do those tests. So you can have some kind of layer where it's not every single person who does something will trigger that, but actually the maintainer will be the one to trigger the CI that will run on the HPC, and that is someone you trust and has access.
And like we can do that within GitHub with like an Archer test merge sort of branch that's got kind of someone a list of people who can approve grant protection and stuff like that. So I think the tooling exists for that, but we are still reliant on identities in GitHub, and GitHub's kind of delegation of authority is outside of the control of your system's identity provider. Is that something people are generally comfortable with?
I say something that comes back to a little bit of what you were saying, and sort of bring it back to your original question about wanting whether this would be useful in CI to do this performance testing. And I guess to some extent, is that a part of CI or not? I'm wondering. I know it's a bit of a cop out for me to answer the question back, but it sounds like there is a need to have this kind of regular performance testing if you're developing code that is supposed to perform very well on a specific HPC. Often we're developing code that we want people to run on different HPCs or even completely different systems altogether. So I'm wondering whether this idea of whether you want to always run these performance tests or whether maybe that should be handled by a kind of some separate project or something. I'm not sure if that makes sense.
I think that makes a lot of sense in a commercial environment where you're doing deliveries of software. The performance tests are usually run at a regular interval, maybe weekly or something like that. And if there's something bad, then you track back to find out what caused the problem. But you don't run the performance tests that have been changed.
I think it's a good chance to flag the High Performance Software Foundation, recently started Soft Foundation, the Linux Foundation. Stack is part of that, and the Stack CICD was mentioned earlier. They are broadening that CICD to be usable by all the members of the HPSF, and I think there's intention to work out how it could be provided as a broader service. I think the underlying HPC that it's running on is being provided kindly by some American university, so I think at this time, that's obviously at risk, and there'll be investigation of how that might be expanded out or other communities taking part in providing that underlying hardware. But there is some form of centralized potential authority that this stuff could be funneled through to try and answer these questions in one particular place. I think HPSF is the sort of foundation where a lot of the software that we use, develop, and so on, doesn't necessarily need to end up in, but should certainly be talking to about these common forms that we have.
My understanding of the effort was that rather than providing to everybody the resources, was to provide everybody the infrastructure, like the workflow, so that it can be replicated somewhere else, but not necessarily the same hardware.
Sure.
But yeah, the infrastructure, yes, that's definitely something that's useful to look at.
Okay, shall we have a look at the other question? Okay, maybe whoever put this question up want to ask it. Do you expect more computing will need dedicated hardware for this and other processes? And I may have lost track of what this was referring to.
I'm going to just throw a question because I think this is maybe it's related to the accelerators. So maybe this one. I've heard of FPGAs, but maybe just throw a question. So is there anybody aware of using FPGAs to accelerate their applications? Because I see this in the C code very well. Maybe you have this special ones. I wonder if you found FPGAs in the wild.
They're not as much in the wild right now. The main problem is just tool flow. High-level synthesis tooling is very much still specialized into non-HPC kind of domains, and the integration between an FPGA card and your high-performance software is it's not just something the GPU have the PCI all that's established. You're doing everything. There is some work. I know Nick Brown did something with, like, I think it was Fortran offload actually on FPGAs. And so there is a community through MLIR from Circuit, which is MLIR down to FPGAs. But again, data transfer is a problem. It's probably going to be not the go. Probably will never be good solid. But I think there are certain workloads where if you can define a custom to cores and that, so something that wouldn't work good on a GPU because you need something very custom, then you might be able to put it here into it. And so you can actually already, if you want to play with it, I think AWS has some Xilinx cards that you can actually rent out instances of and kind of use some simple trials with it. And there is that FPGA testing in C as well.
At CERN, we also use FPGAs. We have like very strict timing constraints for like some ML models for like triggering, like selecting which collisions to keep and which not. So yeah, FPGAs are also used for that kind of workload.
We have a few more minutes before we swap. We have a simple question of performance portability. Does anyone want to comment on what is current state of performance portability? The second one from the top. I mean, so Mode, I mean, I suppose the Julia reactant work is targeting performance portability.
Yeah, the idea was to use this MLIR framework exactly to address the performance portability issue, so that you write your code once and then you have this magic compiler which does the porting for you. I believe there are many other similar frameworks also in other languages which try to do this, like to add an intermediate level to do the porting to other architectures for you automatically. And this is very important, especially MLIR, because it's being adopted by vendors. All the vendors use MLIR at some point of their pipeline. So if you're able to target that, it becomes easier to support new accelerators produced by these vendors. This is one way to do it. Of course, there are many other ways. The question is, what's the current state? I'm not entirely sure, but this is one way to do it. Rely on the compiler, on the compiler technologies supported by the vendors. It's one way to do it.
Okay. Other panelists want to comment before we go to the audience?
I might mention the library level. So if libraries like Cocos or Raja try to target this through providing like generic algorithms for C++ code that you can call, and internally they do some clever interchange based on the architecture you run on. This is one approach. And something like new standards or newer standards like SQL is another approach. But this depends on compiler vendors catching up and implementing that.
Yeah, I guess I've not got any sort of deep insight into the under the hood. My experience has been more on the Python sort of high level side of things, but certainly with that, I think generally a lot of the big Python packages that I mean, like JAX, for example, they use support a fair number of architectures from what I remember, and there's a lot of development with that project. So yeah, my experience is I don't tend to run into too many issues, but I'm not sure about the state of like AMD GPUs with something like JAX. I think I've yet to have tried that because it looked like it was in early sort of stages. So.
Okay, Andy.
Yeah, it's interesting. So when I first started HPC, like all the old HPC people would like just wait long enough and the same idea will come around again, the cycles. And Julia's talk was really interesting because right now, I think this is where I've hit this point. I've been in HPC long enough now. When I first started, performance plausibility was provided by Fortran compiler. Right. So what we did was you went standard compiler, Fortran. You went to a different system. Each system, we had a wide range of architectures then, from RISC and DEC alphas and power and all this sort of stuff. And the vendors provided you with a compiler that optimized your standards compiling code. Okay, and that's how you achieve performance plausibility, right? And that's exactly the same approach we're seeing again, come back again. We've been through a period where it wasn't that plausibility, but it seems to be coming back. It's just interesting that we've come back right now. It's that thing.
Okay. Okay. In the interest of not running into lunch, I suggest we thank Evgeny, Alex, and Mose. We invite the next panel over, and Marion, you're gonna do this.
Yeah, I'm gonna tell this. So we'll have Chris and Matt and Simon over there, and Andy, yes, as well. And then please we have maybe a woman as well there, or a not man. Anyone who would like to talk about a more strategic, more high-level view of the future of HPC, especially in the UK, because that's where we are, but maybe also somewhere else. And maybe we can have a fresh start with the Slido questions as well at this point. Anyone brave enough to take that seat? I will just ask people to briefly introduce which HPC services they represent, and then we'll have a couple of questions around, what might be coming next or what they think about the future of HPC, and we also have Slido questions.
No, I think it's been a really good, interactive discussion. I feel the remote people might be feeling sort of like anyway.
Okay, yeah, we might concentrate more on the Slido then.
Is there a way for them to kind of jump in with conversation the same way, or someone did?
Is this let me
online people hear the room contributions? Okay.
Yeah. So I was surprised by that, but yeah, even if you're in the corner.
So we've got 2 people online.
Okay.
So if you so I can open the chat window here. Oh, if that works.
Yeah. One. Yeah.
Yeah. Okay. So Muhammad is online. So
okay. All right. So then I guess it doesn't matter.
Yeah. I can try to remember. You can remind me to check the chat every now and then. Okay. Still my question. We've got an empty chair. Okay, let's start then. Just maybe going from left to right, can you just briefly introduce yourself and the center or service you're representing, and yeah, what's going on there, and then I'll start asking more questions.
How much can I say about what's going on? How long could I?
Each of you has 2 minutes.
Okay, wow, I think. Cool. Hi, I'm Chris Etzel. I'm representing the University of Cambridge, who run CSD3, the Cambridge System for Data-Driven Discovery, and Dawn. You may have seen our stand outside, and breaking news, all the lions are gone. Come back next RSECon, or come to CIUK or something. So Dawn is part of AIR, my neighbour here. And we are continually expanding the systems that make up CSD3, and hopefully we'll expand the systems that make up Dawn. So this year we've integrated Sapphire Rapids nodes, Sapphire Rapids with high bandwidth memory nodes. We've got a Granite Rapids test node, which has the MR DIMMs. All of these things I'm mentioning are really good for codes with high memory bandwidth requirements. In the Cambridge Open Scale Lab, we've been trialing various interesting architectures. Apparently, we have to give back the 32-bit accelerator. Anyway, we have to give that back. But we've got some AMD MI300X, so I was very interested to hear Motos talk about Oceananigans and Julia running on AMD GPUs. I will be in touch later. In terms of software things, we've been part of some awards recently. So the NFCS Network Plus Award, National Federated Computing Services. We're in the collaboration with Federated Authentication. We're in a collaboration about AI containers. So how would you run a container that ran on both Dawn and Isambard AI and maybe future air systems. Marion has won an award for CAKE and for Computational Advanced Knowledge Exchange. So this is the activity that was originally in Excalibur and has been so useful that it's being continued. You can ask Marion about that. And we're doing work on TRE, Trusted Research Environments, with the Fringe and Veros AI projects.
Thank you.
Cambridge.
Hi, I'm Matt Williams. I work for the Bristol Centre for Supercomputing at the University of Bristol. We have a number of systems, all of which are quite new. So we have Isambard AI. They're currently, I always don't like saying the fastest, but they're currently the fastest supercomputer in the country. Only for a while, given that funding for other supercomputers has already been announced. Coming on to that soon, I'm sure. We run, as part of the AI research resource, along with Dawn, a couple of the grants and projects that Chris has mentioned. We're affiliated with them, so I won't repeat on those. But being a new system, we only officially launched about a month ago, so we're still in the early stages of establishing exactly what kind of user experience that we're going to be looking at. Being an AI-focused center, we're really trying to think about what kind of experience people want to have with these systems. At the very least, going container first, but thinking about interactive compute and other ways of interacting with supercomputing systems. So over the next year or so, I think a lot of our focus is going to be on programmability of how you interact with systems, movement of data, workflow management, things like this. That's all going to be coming on over the next year or so. And talking of awards and grants we have, I should plug one of them that we have, which is called the Advanced Computing Infrastructure Training Hub. Basically, a big grant to train system administrators for people who run GPU and other accelerated computer systems, because it's hard to hire, and so we're trying to make sure that we're training the next generation.
Hopefully I'll be quite quick. Hi, so I'm Andy Turner. I'm from the PCC. EPC is the UK's National Supercomputing Centre. We run a few of the national services, or involved in a few national services. The main one, which we mentioned a few times, is Archer 2, which is badged as the UK National Supercomputing Service, but is really funded by HPCRSE and NERC. So for those people who are onto the UK, that means it's focused on engineering, physical sciences research, and natural environment research. We're also involved in DIRAC, which is the STFC-funded National HPC facility, for that's particle physics and astro and cosmology. And we run a large GPU system called Tersa. So in terms of what's coming down the line, as Matt mentioned, there was an announcement from the government back in June, I think it must have been now, that there was 750 million, up to 750, they're keywords in that sense, up to 750 million pounds to support the next national supercomputer, which will be hosted up in Edinburgh. I don't know a huge amount about that right now, right? Not because I'm not privy or I'm not allowed to say anything. It's just the government haven't said any more other than that announcement, even to us, about what that's going to look like and when it's coming. Rough timescales. They hope to kick off procurement either in the next quarter this year or the start of quarter one. I think the earliest that system will be available will be like quarter 2 2027, something like that. So that's where we are.
Thank you, Simon.
Hi, I'm Simon Burbidge. I work for Direct. So thanks, Andy, for taking some of your time to say what Direct is and what it does. So I don't need to repeat it. I'm an HPC person, basically through and through for donkey years. The interesting thing, I think, for me and the work we're doing at Direct at the moment is the challenge of adopting accelerated computers for large-scale research. The easiest stuff has all been done, so it's just hard stuff from now on. And as Andy said, for the past 20 years, everybody's got very much isolated into very simple ways, and almost portability hasn't been that important, but now it is becoming again. And I'd like to make sure what we do now, and a lot of this work is being done by RSEs, is to make sure what we do is good for the future, and the methods and the techniques and the information we get is portable and it's useful for future development as well.
Can I want to say, otherwise I'll be in deep trouble getting back to this. So the other thing that's happened is that the Research Council's UKRI have funded quite a large benchmarking development project. It's about next generation HPC benchmarks that are maintained and supported over a longer period of time and can be used for assessing performance portability, for example, profiling and understanding what the community needs, and being used for future HPC system procurement. So that UKRI Living Benchmarks project, it's ongoing. We're out talking at the moment to people about what benchmarks are out there for research across UKRI, not just science. And if you have ideas or your community has ideas for benchmarks that should be included, particularly if they represent areas that we'll struggle to touch because we don't know they exist, because they're not traditional users of HPC, we're super interested in hear from you.
Okay, thank you. I'll ask again, anyone who would like to sit on that remaining chair, they don't need to make a big introduction. Okay. But please put in your questions to the Slido, so I don't have to come up with all the questions. But I would like to ask, or start by talking a bit about the UK Compute Roadmap that came out in July, I believe. So I've read through it, and as probably with most of long documents you read, there's mostly one thing that stays in your mind and that you keep reminding. So I would like to ask you whether you have this one thing that you want to point out and want to say your opinion to. So my thing was, apart from AI was there was in this roadmap that was put on there for 2026, they announced a grant software challenges and skills program. I've not been able to find more information than this one line in this document. I talked to some people at UKRI and they said, oh, yeah, we're still figuring out the finance and so. So if anyone knows anything about this, please tell me. No? Okay, do you have something that you've taken out of this roadmap document? Yeah.
I think maybe one of the things that just came to mind immediately was I might get the terms of this one, the idea that the government wants to designate new national supercomputing centres, is that the phrase they're using? Of which EPCC is the first, announced, but the fact that they are committing to do more to diversify and delegate out around the country centres of excellence in HPC and not just focus their energies just onto incumbents necessarily or onto a single site, I think is a really a good sign that they're maybe thinking again about diversifying things out, given the lack of investment in tier 2s, for example, in a long time. this is maybe their approach again to try and set up centres that are able to have different identities around the country to provide those sorts of experiences.
Yeah, thank you.
Yeah, I think I agree. I think that is the key thing that's been missing from the UK in terms of HPC, like DRI more generally, is a more strategic approach to planning it, right? There's often been sort of funding that appears short term, we have to spend it to have particular experience of this pain. And then there's some sort of artificial competition that sets all people who are experts in this, and we all work together, right? And we're all very collaborative against each other for a short period of time. So we walk around sort of giving each other side. And stuff like that for a short while. It feels really uncomfortable and really counterproductive in lots of ways. And I think the national supercomputing centres are hopefully a way to address this, and a vehicle for allowing a more strategic way forward, a different way of putting funding in that doesn't result in competitive calls, that allows people to pool their expertise and keep the community going in a more sustainable way going forward. I think that's critical, right? That's the bit the UK has been missing, is that strategic thing that a lot of our peer countries around the world do have and manage much better than us.
Okay.
I would add, I think, Marion, you put your finger on it, your analysis. It's all of AI, but the really nice thing is there is a mention of skills. And I think we're quite lucky in the UK in that the RSE community is leading and is bigger and more recognised than in many other places. But that the government has actually said, shiny great pin, AI, but it's actually got skills, which means people. So I think that's a positive step.
Yeah, just would have liked to see a bit more about how.
Yeah.
I'm not asking how they do stuff. You have to do. It's up to us to work out how.
Yeah.
Yeah, I think my question is just related to this whole strategy that you're going on at the moment. Even the amount of public funding that goes into our supercomputers is minute compared to, first of all, the private sector, the big companies, and compared to international funding that goes. As a nation, what strategy should the UK community adopt in order to maintain some level of confidence? In reality, the funding, 750 million.
Anyone wants to take that? Chris.
I don't want to take it because I don't have an answer. It's certainly a problem. So I was talking to a researcher recently who was in a meeting with Yann LeCun, who was explaining how he managed to strong-arm the French government into spending more money on GPUs, because the French government were talking about Jean Zay, their supercomputer, and Yann LeCun said, my intern has more GPUs than that. And so basically getting industry to shame the government into providing a decent amount of HPC resource. So the document you're mentioning is talking about 20xing the UK's GPU provision by, I can't remember,
30 maybe?
Yeah. It's a drop in the ocean. It's not enough. Also, 20, say it was 2000xing the GPU provision. What does that then do for sustainability? Because these things are quite energy intensive. So I don't have an answer to your question, I'm afraid.
One interesting thing, I guess, is if you're the UK government looking at investment in supercomputing and HPC the past year, you're like, actually, our strategy really works quite well because we don't put much money in. We have massive impact compared to the amount of money that other countries put in. And so they're looking at it going, well, these guys are all great. They can do it all on a shoestring. And so, people here who run these services are all running around and doing amazing jobs. RSEs are all doing amazing jobs on little funding and producing this sort of miracle. Now, the question then is that sustainable over the long term, right? And I guess the reality is that gets tested in whatever level of funding the government puts in. If they put more funding in and it gets that much more better, great. But if they put less funding in and we still manage to maintain it, they're going to go, well, that was a pretty good choice for us, you know, in terms of investments. So we've done a lot through our expertise and the people, I think, more than the hardware. You know, we get a lot out of our hardware because of the expertise of all the people who work on it. So I don't think that I'm arguing that we shouldn't be pushing for a bigger investment, but I am, you know, I think government do recognise that we do very well, or at least the people who are close enough to this recognise that we do very well and have a large impact for the amount of investment they put in, which does put us in a bit of a sticky situation in terms of asking for super linear funding.
We've got like 1 minute left and lots of questions. Let's try to quickly, I let one person answer very shortly. So is there an alternative to AMD for traditional HPC non-AI systems? One sentence answer from any of you.
Yes.
Yes.
I mean, really, it's too expensive.
Okay.
Potentially, I mean, list prices.
Next question. Do you see HPC centers in the UK be more unifying in the future, so that people could have one allocation and then just pick and choose where to use it? And I think there was a follow-up on that one that I've. Okay.
Yeah, I think that briefly. So we're doing a lot of work at the moment under a number of funding projects about federating out DRIs, number of Network Plus projects, and just individual experiments going on at the different centres to federate out identities, allocations, data transfer, things like this. We want to have the ability for anyone to be able to move their data from system to system. In principle, maybe allocations from system to system, if that's something the government wants to do, but certainly to have all the systems have a common understanding of who you are and what you're allowed to do. That's actively something that's being worked together at the moment.
Thank you. There is a question about sustainability in terms of maintaining existing systems. I know that Lydia Heck did a very nice second-hand hardware thing a couple of years ago, but is there any consideration, or do you know anything about sustainability in this?
I think we should really work on that and do the calculations that say what computing and what output are we getting from those older systems compared to how much energy and how much it would cost to replace them, both in terms of the people type but the carbon footprint and that stuff. We can do the math.
Energy plus embedded carbon, but the thing Andy was saying.
Yeah, I mean, it's clear we should be running our hardware for longer than we have done. It typically have done in the past.
Yeah, not chasing the next 500 maybe, but
UK, until there's more AI, UK hasn't been chasing top 500 positions for.
Yeah, and like those old GPUs can do certain work just as well, just efficiently, less expensively than the new ones. So maybe it's
and help us with the CI/CD issues that we have, because we don't need the newest flashy hardware to do CI/CD.
So I'm really, really sorry that we did not put more time down for this panel. So please grab the speakers if you want to discuss further. Please come back after the lunch break for the training and community part of this session. And thank you very much to the panel.